This is a demonstration of a natural language understanding system applied to the limited domain of controlling a simulated robot. It was developed by the International Computer Sciences Institute, ICSI, and I'm going to put it through its paces and then we'll talk about what's underneath the covers. So first let's ask the robot to move to the green box. While it's doing that, get ready to ask it something else. So it understands how to move. It also understands how to dash, which means that it understands multiple different verbs as parameterizations of the same underlying motion. So let's ask it to amble to the big red box. It also understands, in addition to ambling as different from dashing and moving, it understands adjectives that qualify which box we're going to go to. Let's see if we can get it to stop in time. So, and we can interrupt it in mid-trajectory there. And let's tell it to pick up where it left off. Finally, we can tell it to do something completely different in the middle of a trajectory, and it'll pick up the new command and execute that. All right, so that's our little toy demo. Let's talk about what's underneath the covers. So here's a high-level picture of the architecture of the system we've just seen demoed. We have the world at the top, and then let's think about it as a left side and a right side, a language side and an action side. I'm not going to get into the details of all the components. I'll just say that the only thing I've done any significant work on is the box in orange that says actions and Xnets. But on the left side, we have some language coming in this case, robot 1, stop moving. It goes through some processing to extract the meaning that's inherent in the statement. But there's a whole world that isn't contained in the text that we have to have reference to in order to solve the problem that the language suggests to us. We're going to represent actions using the PetriNet formalism that I've described previously, so I'll just go over it very briefly. We have places or states shown as circles, and transitions between those states shown as rectangles, and the arcs show the flow of control. We'll show this working briefly, but if we look at this, we might consider this to be a schema for how motion might get handled in two dimensions. And if we have a sentence, for example, robot 1 moved to the blue box, we're gonna start from the left and work our way through. But before we show that example, I want to talk about what I think of as the standard semantics of this structure. So it's a PetriNet, but we've given it a structure that we think is appropriate for events and for actions in particular. And the stuff that is highlighted in gray are things that we think are common to all events. They have some enabling condition. They get ready to run. They have some ongoing state that might last for a good while. Eventually they finish and are done, but they might get suspended or restarted or resumed. Those are semantics that come from language. It's about how we think about events. And in particular, there's a concept of aspect in linguistics which captures the notion of things that are about to happen or are happening or have just happened, and that maps well to this structure. So those are our standard semantics. The stuff that's not highlighted down below is specific to motion, and we've given a very simple notion of moving, move a little bit, and we've moved, and we wait a little bit, we move a little more, some loop around moving until we've arrived at our destination. So that's the overall picture. Let's see this in action. So a normal flow here for this particular executable schema, which we implement as this PetriNet, which we'll call an Xnet, starts with marking with a token the enabled place. And then we follow the arrows, we go to ready, and then we branch through the start transition, and we mark both the moving, which is the specific action that we're representing here, and ongoing, which is a general statement that we're doing something. And we loop around in the moving loop until finally we arrive at our destination. At this point, all three of the arrows that go into the finish transition are connected to marked places, and therefore the finish transition will fire and we're done. Okay, that's the normal flow. Supposing we had a command in the middle of a motion, that is to say we're in ongoing motion, but we want to stop moving. And we would mark the suspend place, and then we'll transition to suspended, and the robot will stop. Notice that we've got two different sentences around motion that have very different grammatical structure and meaning, but we represented them with the same schema, just different markings at different places. This is the economy of this formalism for representing action. Allows us to make inferences about what might be going on at a particular point in time and deal with it appropriately. So here's another case. Supposing we say, okay, robot 1, we'll continue moving. Well, we can only continue if we've already stopped. And so we're in the suspended state. We mark the resume place, and we transition back to ongoing and pick up where we left off. Last case, this is more complicated. Supposing we were already moving, but now we've got the command that we showed at the end of the demo to move to the blue box instead of the red box where we were originally headed. So we're ongoing. First we suspend, but we're going to want to restart our motion to some new location. So we've marked two places here, and we go through two transitions. First we go to suspended, and then that enables us to go through the restart transition. We go to ready, and we pick up the new target location, and we keep going. So now we're back in ongoing. Notice that two things are marked in our moving loop, and that represents a simplification that's possible because of the way we interface to the Morse simulator. We're just giving it an initial motion, and then every time through the loop we just update our position. That helps us know when we've arrived. So that's a simplification that has to do with how we talk to Morse, but it brings up the overall question of how are we talking to the larger language system and to Morse. What are our external interfaces? This is actually the area where I made a contribution. The stuff that's in blue here are ways of talking to the outside world, outside the Xnet, and vice versa. Let me go through those briefly. The dotted rectangles show external transitions instead of just ordinary transitions that fire and move tokens along. This one, these can invoke any arbitrary external logic. In this case, this is a way for us to handle the parameter passing. So we've talked about the state changes of stopping, continuing, changing direction, but we haven't talked about how we handle the parameters of what's the difference between dashing and ambling and just moving and location. Those are actually being handled through these external transitions where we have a data structure we pass around that I'm calling the Morse channel that passes in the parameters, allows us to update parameters and talk back and forth to the Morse robot. So that's one mechanism of external interface. The two sets of boxes with the with the triangular arrows there indicate either places that are marked by the external system, that is input from the external system, or a place that's read by the external system. So something that's marked by the external system, for example, in the lower right, is the arrived place, which indicates that Morse has detected we've arrived at our location, marks it, and that's the signal that we're going to be done. Places that are read by the external system are places like ready or ongoing or done or suspended, and those are primarily, but not exclusively, the places defined by the standard semantics that will allow an external system to make general kinds of queries. Are you done? Are you ongoing? Have you not even started yet? That will ask over and over again about actions and events. So those are the things I've added on top of the basic PetroNet system, and that enables this to participate in the larger natural language understanding system. That's our demo. But before we end, I should point out that my contribution was built on the contributions of many people, and I've listed a number of them here. The list isn't complete, but there wouldn't be anything for me to contribute to without all of this other work. So I hope that was interesting, and thank you for listening.